In level 3, we will be solving trig equations containing a single trig function. And for these, instead of using inverse trig functions, we're going to be looking at angle values on a certain interval. So in this example, we're supposed to look for x values between 0 and 2 pi. When we solve a trig function, or a trig equation, we are going to start by isolating the trig equation. A lot of our solving equation rules will apply. So I want to get sine x by itself. First, I would add 1 to both sides. And we get 2 sine x equals negative 1. Then I divide both sides by 2. And we get sine x equals negative 1/2. And then now the question is, where on the unit circle from 0 to 2 pi do we have sine values of negative 1/2, which angles? And those angles would be 7 pi over 6 and 11 pi over 6. In the next example, I want to get cosine of x by itself, so I'm going to add 1 to both sides. And we get radical 2 cosine of x equals negative 1. Then I'm going to divide both sides by radical 2 to get cosine by itself. And we get cosine of x equals negative 1 over radical 2. But I don't want to leave my radical in the denominator, so I multiply by root 2 over root 2, and I get cosine of x equals negative radical 2 over 2. And so now I ask myself, where between 0 and 2 pi do we have angle measures that have cosine values of negative radical 2 over 2? And those angles would be 3 pi over 4 and 5 pi over 4. In this next example, we can use the zero product property. If we have two factors and the equation is set equal to 0, we can figure out what makes each part 0, and that will give us our solutions. So first I'm going to see which values of x make cosine of x equal to 0. Cosine of x equals 0 at pi over 2 and at 3 pi over 2. And then the second part of this problem is determining when 2 sine of x plus 1 equals 0. So we solve this equation also. I subtract 1 from both sides, and we get 2 sine x equals negative 1, divide by 2, and sine x equals negative 1/2. And now I think between 0 and 2 pi, where do we have sine values of negative 1/2? And that is 7 pi over 6 or 11 pi over 6. So we get 4 different possible x values that make this equation true. In these next examples, we have a tangent squared x and a cosecant squared x, but we're still going to solve by isolating the trig function. So in the first one, I want to get tangent squared x by itself. So I'm going to add 3 to both sides. And we get tangent squared x equals 3. And then to solve this, it's kind of like having x squared equals 3. We would take the square root of both sides and remember to put plus or minus on the side with the number. We're going to take the square root of both sides, put a plus or minus in front of the square root of 3, and that cancels out the square, so we just get tangent of x equals plus or minus the square root of 3. So now we need to think of the places on the unit circle that have a tangent value of either positive or negative radical 3. And to get a tangent value of radical 3, we need our y over x to be root 3 over 2 over 1/2. That gives us root 3, or it could be one of those negative. So this can happen in all 4 quadrants of the unit circle, And the places on the unit circle where we have a big y and a small x are the radical 3's. So pi over 3 has a bigger y, a shorter x. Also 2 pi over 3, 4 pi over 3, and 5 pi over 3. All four of those places have a tangent value of radical 3. So x can be pi over 3, which has a tangent value of positive radical 3. 2 pi over 3 has a tangent value of negative radical 3. 4 pi over 3 is positive radical 3, and 5 pi over 3 is negative, but it could be positive or negative. So all four of those angles are solutions. The next one we'll solve the same way. We want to get cosecant squared x by itself, so we add 4 to both sides. And cosecant squared x equals 4. And then we square root both sides, and we have to remember plus or minus on the side with the number. And we get cosecant x equals plus or minus 2. Now, if cosecant x is plus or minus 2, remember cosecant is the reciprocal of sine. We're looking for the places where we have a y-coordinate of 1/2, because if I flip that, we get a cosecant value of 2, and it can be positive or negative 1/2. So on the unit circle, the places that have a y value of positive or negative 1/2 are the angles that have a reference angle of pi over 6. So pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. All of those have a y value of either positive or negative 1/2. So x can be pi over 6, 5 pi over 6, 7 pi over 6, or 11 pi over 6. And one more example in level 3. We want to get tangent x by itself, so we subtract 1 from both sides. And we get radical 3 tangent x equals negative 1. Divide by radical 3 to get tangent x by itself. And we get tangent x equals negative 1 over radical 3. We don't want to leave the radical in the bottom, so we multiply by radical 3 over radical 3. And we get negative radical 3 over 3. So we want to find the places that have or the angles that have a tangent value of negative radical 3 over 3. Now this time we're looking in all real numbers, meaning not just the unit circle, but all values of x that give us that tangent value. So first let's think about the unit circle where this happens. To get a tangent value of negative radical 3 over 3, we need y over x to be 1/2, well negative, over root 3 over 2. That gives us negative 1 over root 3 or negative root 3 over 3. So the places on the unit circle that give us a tangent value of negative root 3 over 3. First of all, tangent is negative in quadrants 2 and 4. So we're not looking in quadrants 1 or 3 because they're positive tangent values. And the places where we have a y value of 1/2 and an x of radical 3 over 2 are the pi over 6's. So at 5 pi over 6, we have an x of negative radical 3 over 2, a y of 1/2, and also 11 pi over 6. We have an x of positive radical 3 over 2, a y of negative 1/2. So those are the two places from 0 to 2 pi that give us a tangent value of negative root 3 over 3. But we want to list all the places on the unit circle. So say I start at, or not just on the unit circle, in the whole real number plane. So if we have 5 pi over 6 as our first angle. And then our next one is 11 pi over 6. And then if I make another half circle, I get back to an angle coterminal with 5 pi over 6. Making another half circle, I get an angle coterminal with 11 pi over 6. And so what we can do is just 5 pi over 6 plus any number of half circles, and we call that pi k. So any multiple of pi where k is some integer. And that would be all the angles that have a tangent value of -√3/3.